In Córdoba, a city in the southern Spanish region of Andalusia, battling extreme heat has a long history. As far back as the Roman period, residents began designing inner courtyards with plants and fountains to help manage temperatures during heat waves. This architectural approach is still in use today and continues to effectively reduce indoor heat. However, as climate change progresses, these traditional methods alone may no longer be enough. In just a few months, a new district heating and cooling network has been set up at the University of Córdoba's Rabanales campus. This facility acts as a living laboratory where students and researchers can test different technologies aimed at reducing carbon emissions from building heating and cooling systems. The main buildings involved in the tests are the Monte Kronos Sports Stadium, which focuses on warm water systems, and the Da Vinci building, addressing both heating and cooling systems.
Uno de los retos más importantes del proyecto es combinar diferentes tecnologías.
One of the most important challenges of the project is to combine different technologies and operate them, to identify which combination of technologies allows for the best efficiency from both an energy and an economic standpoint, in order to provide year-round climate control to buildings. In the case of the pilot plant at the University of Córdoba, there is an additional challenge how to supply cooling to buildings in a renewable way. This is a challenge that only we, the countries of southern Europe, face.
Es un reto que solamente lo tenemos los países del sur de Europa.
Córdoba's nearly 3,400 hours of sunshine per year make it an ideal location for using solar energy. The facility is therefore equipped with a mix of advanced solar thermal technologies, including parabolic troughs, Fresnel collectors, and the newly developed flat plate collectors with adaptable mirrors.
One of the innovative aspects consists of a completely autonomous tracking and motion system for the collector, with a photovoltaic panel that we can see in the central part of the collector. The system can use solar energy to power its own movement, as well as to control its position relative to the sun. These collectors are always used to produce thermal energy.
The Fresnel collectors, for example, use flat mirrors to concentrate sunlight onto a central tube filled with water. As the sunlight hits these mirrors, they reflect and focus the light onto a central tube. The water inside the tube heats up rapidly, and its thermal energy is then transferred to a 50,000-litre storage tank. This tank can keep the temperatures up to 95 degrees Celsius, hot enough for various uses, such as hot water for domestic purposes in nearby buildings or to power cooling systems. But what happens when the sun is not shining? To ensure a continuous supply of heat, biomass boiler systems operate alongside the collectors, stepping in when sunlight is scarce.
This booth integrates biomass boilers, each with a capacity of 500 kilowatts. Additionally, inside each of them, there is a set of electrostatic filters that help reduce emissions to minimal levels. Different types of biomass fuel can be used, such as almond shells, olive pits, wood chips and pellets.
Another key feature of this pilot plant is the Renewable Air Cooling Unit, short RACU. This system efficiently manages indoor comfort and cools down temperatures during heat waves. To achieve this, the RACU combines two technologies. It starts with a drying wheel based on silica gel that removes moisture from the incoming air. Afterwards, the temperature of the dehumidified air is reduced by a cooler unit. Simultaneously, the drying wheel is regenerated by another heated airflow, making the wheel dry again.
The main advantages of this RACU prototype are that it uses 100% outdoor air, unlike conventional systems that rely on a high percentage of recirculated air. In addition to its low energy consumption, this also reduces environmental impact with a highly sustainable technology that maintains optimal thermal comfort and air quality.
Researchers expect that the new system will reduce CO2 emissions by 80 to 95% compared to conventional air conditioning systems. However, implementing such innovations can be challenging, especially in commercial plants where operations must continue without interruption.
Al ser una planta en un entorno universitario, en un entorno de investigación,
since it is a plant located in a university environment within a research setting for the industry, access to testing components is made much easier. For example, different qualities of mirrors, absorber tubes, storage systems, temperature measurement systems, and flow meters can be tested more conveniently. Therefore, within this W.E.District plant at the University of Córdoba, we see that the industry will have greater ease in testing new technologies, which can later be implemented in commercial plants.
Para probar nuevas tecnologías que luego podrán ser implementadas en plantas comerciales.
The pilot facility will now start operating and be further evaluated by the university students and researchers. This will help determine which technologies are most effective in reducing carbon emissions from district heating and cooling systems, especially in Europe's most challenging climates.